Now it's time for the fully general version of K, and this will wrap up what's called the Poincare Lemma, which is that if you're in all of Rn, then a closed form is necessarily exact. Any closed P form, as long as P greater than 0. Otherwise, it's not possible to be exact. So, remember we have this definition of K with some integrals. We want to show that the difference between alpha and its smushed version is up to a sign dk alpha minus kd alpha. So the interesting thing is dk minus kd, that combined operator. So, two cases. The first one is where the last coordinate, I'm going to take dk of this kind of building block, a function times a certain wedge of the dx's, and I'm going to assume that the jp really is n plus 1, so that the dx n plus 1 is included in here. And I'm going to take dk of that. I'm going to see what happens when I evaluate that at a point x1 through xn plus 1. So that's going to be d of, well, here's the k. This is the one where k is not equal to 0. It strips off the dxjp, leaving a dxjp minus 1, just like up here, and then integrates the coefficient function from 0 to xn plus 1, and there's the variable of integration. And then I still have to take d of that. So I'm going to take the sum, I equals 1 to n plus 1, this is in Rn plus 1 after all, of all the partial derivatives of this integral, then put in the dxi and put in all these guys. As usual, if the I collides with one of these guys and it happens to be 0, no big deal. It doesn't have to be treated specially. It's wonderful. Okay, so there's a difference between whether this is dx n plus x n plus 1 or the other dx's. If it's not xn plus 1, then it just moves inside the integral. We've seen this a few times before in the last few videos. If it is, then the fundamental theorem takes over, and I just get f evaluated at x1 through xn plus 1, dxn plus 1, which all this stuff. That should look very similar to this. The only thing is that the n plus 1 is in front, but that just is going to create a sign. Okay, let's not worry about it quite yet, though. Okay, so now, let's go down here. Okay, now what about kd? Okay, well, we'll take d, which is the sum of all the derivatives, and now I is going from 1 to n. The reason for that is that I know jp is n plus 1, so I don't need to explicitly include the df dx n plus 1, because I know that will die, and it's going to be a better match for this if I remember that that's going to die. So k of a sum is the sum of the k's, is defined by linearity, and what I'm going to do is I'm now going to integrate this df dxi function with a variable last coordinate xn plus 1 set equal to t. Remember, the jp is xn plus 1, so this is the case where k doesn't kill it. It actually does this integration process. But it does strip off the dxjp and becomes a dxjp minus 1. Okay, so let's look at what we got. This stuff is exactly equal to this stuff. Once I pass the integral inside, it's the same thing as if the derivative. It's the same thing as the derivative started out inside. So if I subtract them, everything cancels off except this part, which is pretty close to what I want. It's pretty close to alpha, but I just have to skip the xn plus 1 past p minus 1 variables. So I'm going to get minus 1 to the p minus 1 times alpha. Now what we wanted really was that it was minus 1 to the p minus 1 times the difference of alpha minus its smushed version, its simplified version. But remember, when the last coordinate is included in this guy, the z kills that right away, and so alpha is the same as alpha minus cz alpha. So the dk minus kd is up to sign the difference of between the alpha and the cz alpha. Awesome. Okay. Now, what if the last coordinate isn't n plus 1? So a dx n plus 1 is not part of this. Well, then k just kills this thing. That's an easy calculation. If I instead take d first, and I'm going to need to be careful about the point of evaluation, eventually, I look at the sum, all the derivatives, all the way from 1 to n plus 1, df dxi wedges into the rest, and, well, let's see. I'm going to take k of this. If the n plus 1 is not included, it wasn't included in the jp, so the only thing that could possibly make it not die is if I is equal to n plus 1. So the sum collapses to just partial f partial xn plus 1. And then at the same time, I went ahead and put the dxn plus 1 at the end. That's skipping over p different indices, not p minus 1, so we have to be a little careful. That's p different things. So I get minus 1 to the p times k of this thing. Now, I'm going to actually act with k on this. Minus 1 to the p is still there. integral 0 to xn plus 1 of this partial derivative. Guess what? That's the other version of the fundamental theorem of calculus. And I get the difference between f evaluated where I really want it to be evaluated and f evaluated with xn plus 1 set to 0. Hey, let's see. If I take dk minus kd, all that does is 0 minus this. That turns it into a minus 1 to the p minus 1. F times this wedge is exactly what I started with. That's alpha. And the f with the xn plus 1 set to 0 is exactly cz alpha. And so I get exactly what I need in both cases. Okay, so now let's wrap it up. What was the deal? Let's look at the equation that we've just shown is true in all cases. We showed it for the two building block cases, and therefore by linearity it's true for everything. And that was where this version of it was very nice, that we could do building blocks in the linearity. Okay, so if alpha is closed, if alpha is closed, okay, then d alpha equals 0, and hence this simplifies to alpha equals let's just copy it and kill this part. All that this dies, okay. But cz alpha, remember by the induction hypothesis, z alpha was closed, hence exact in Rn, and c z alpha is then c of d, let's call it beta, just like we had before, which is d c beta. Okay, and so therefore alpha is d of the quantity c beta, that comes from the induction hypothesis, plus this sign, which we don't really care at all about, k alpha. So kind of a complicated argument, and certainly the details of the integration stuff were complicated, but this is really the core of the idea, is that this part was smushed down into the previous dimension, and we used the inductive hypothesis to get this beta, and then brought it back up using c, and so c beta is part of the story. This is kind of gives you the exactness on the first n variables roughly, and then to take care of the new variable, that's what the k was. You took alpha, you did this funky integration trick in the last variable to get the exactness, to take care of the exactness in the last variable. So this whole combination is something that if you take d of it, you will recover alpha, given that we assumed that alpha was closed in the first place. Pretty cool. And I'll save the rest of it for another video.